And the share. So, chapter E, which is what we have been doing, focused on some skills that you would need throughout the semester. Those skills included understanding significant digits, doing calculations with significant digits. Those skills involved density and working with density, temperature and working with temperature, and then also general idea about dimensional analysis. Now, I'm excited because chapter 1 starts getting into good stuff for me, which is the chemistry. Chemistry, by definition, is the study of matter, its properties, and their transformations. So the basis of this is matter. Matter is anything that has mass and takes up space. That's why chemistry, it varies from discipline to discipline, but that's why we as chemists think that chemistry is the central science, because everything, including the air you're breathing, has matter and takes up space. So literally, biological systems, the food you eat, the walls that this room is made up of, all of that is chemistry and chemical engineering. So that's why we often refer to it as the central science, because everything contains matter. Now, we can classify matter using a variety of tools. One tool that we can use is we can talk about something with respect to its state of matter. Is it a solid? If so, it's going to have a definitive mass and it's going to have a definitive shape. The particles, all they're going to be able to do is sit there and vibrate. They cannot move very much. Is it a liquid? If it is a liquid, that means that it has a definitive mass, but it's and it has a definitive volume, but the shape is going to be that of its container. It spreads out. Now with liquids, they are not held, the particles are not held as tightly to one another, and therefore they're allowed to flow over one another. And then you have gases. Gases expand to fill whatever volume is available to them. There is a huge amount of space between gases. Because of this huge amount of space between gases, there is no interaction, or we consider it to be negligible. So we can classify matter according to its state. But the classification of matter according to state really is not very descriptive. Because I see a large number of solids in this room. I see several liquids in this room. And I know this room has several different gases in it. So that being said, this just describing something by its state of matter is not very informative. So let's look at another way we can classify matter. Matter can be broken down into pure substances, and it can be broken down into mixtures. A pure substance means that there's only one type of thing present. Pure substance means that there's only one type of atom or one type of molecule present. A mixture means that there's more than one type of atom or more than one type of molecule present. There's more than one type of substance present. Now, pure substances can be further divided. They can be in the form of atoms of elements, or they can be in the form of compounds. Not on this periodic table, but on this periodic table. Every element that is known to man or known to people is on this periodic table. Yes, we are still in the process of colliding two different atoms of elements at extremely high speeds and creating new elements. But as of right now, these are the only ones that we have been able to quantify and say, yes, it does exist. Now, some of these elements exist strictly as an atom, a single atom. Some of them exist as molecules. For example, oxygen. Oxygen in its natural form always exists as O2, meaning there's two oxygen atoms. It exists as a molecule. Another example of an element that exists as a molecule is going to be graphite. It's nothing but carbon atoms, but they exist as a molecule. So elements can either exist as single atoms or they can exist as molecules. Whereas a compound is a substance that consists of more than one type of element in a very specific ratio. Water is an example. No matter where you obtain water, it will always exist as two hydrogens and one oxygen. No matter where you obtain rust from iron, it will exist as two irons and three oxygens. So you have your pure substances. And then you have mixtures. Mixtures can be homogeneous mixtures or they can be heterogeneous mixtures. Basically, whether it's homogeneous or heterogeneous is all dependent upon the composition. Is it a uniform composition such as coffee, tea, and a variety of other things? If it's a uniform composition, meaning that no matter where I take my sample, it's going to be the exact same, then it's a homogeneous mixture. Also sometimes referred to, well, frequently referred to as a solution. The air you breathe is a homogeneous mixture in an ideal situation. Now, I would wager that it's probably no longer homogeneous because you breathe out carbon dioxide. So I'm going to guess there's a little bit more carbon dioxide right here at any given time. But in general, the air we're breathing is homogeneous, which is great. Because if it wasn't homogeneous, then 78% of this class don't want to breathe nitrogen. Because only 21% of this class is going to get to breathe some oxygen. So homogeneous mixture just means that it's a uniform composition. Whereas a heterogeneous mixture means that it's an irregular composition. If you take sand and water and you are talking about going into a lake, for example, that sand is more sand, but as you go deeper and deeper, you get more water. It is not homogeneous, no matter where you're at. So we're going to talk about all of these a little bit more. Again, all elements known to man, known to people, are found on the periodic table. The one I handed you is the most up-to-date version that we have. Now, as we progress through the semester, we're going to delve into this periodic table more and more and understand its structure, because the periodic table is the most predictive tool that exists. It can predict what an unknown element is going to behave, how an unknown element is going to behave. Now, on this periodic table, some of the divisions. The first thing I want to talk about is this light blue region, which is boron, silicon, arsenic, and germanium, antimony, and tellurium. Those for certain are metalloids. Now, polonium and astatine, people go between those. This particular one, and I believe your textbook does it as polonium. Now, that knowing those are important, not for this upcoming test per se, but for future exams. Because everything to the left of those metalloids are metal. And if you look at this version of the periodic table, you would notice that everything to the left of those metalloids has a plus charge. They all form cations. Metals always form cations. Metals always form cations. They never form anions. Now, the anion, the job of the anion is related to the nonmetals. Nonmetals form anions. And some of the metalloids as well. But nonmetals primarily form the anions, meaning negatively charged ions. Some of these have very specific names. Group 1 is known as the alkali metal, AlKali. Group 2, and that group 2 is known as the alkaline earth metals, AlKaline, earth, metal. That's because the majority of those came from the earth, were found in materials on the earth. Group 17. The next to last group are known as your halogens, Halogens. And when they form a negative charge, they're called halides, Halides. And then your noble gases, which is group 18. They're considered noble because until you get to really xenon, I think there may be a couple of compounds that contain krypton, but for the most part, you got to get to xenon before you find a noble gas in a compound. This periodic table has a lot of information to it, which we'll discuss more here in a minute. So again, the difference between atoms is an atom is a single substance, a single atom of an element. Molecules, you will notice that a molecule also has the same element, but there may be more than one of that element. But compounds contain more than one element in a very specific ratio. You alter that ratio, you alter the identity of the compound. Water has 2 hydrogens and 1 oxygen. If I alter that ratio to 2 hydrogens and 2 oxygens, now I have peroxide. One you need. The other one your body specifically tries to get rid of. So again, compounds are elements combined in a very specific ratio. They follow what's called the law of definite proportions. I keep giving the example of water. It has 2 hydrogens and 1 oxygen. The formula of the compound tells you how many of each element is present. So there's 2 hydrogens and 1 oxygen. When you don't have a subscript, it means there's 1 of them. With methane gas, methane contains 1 carbon and 4 hydrogens. Again, the formula is telling you the exact ratio for that substance. And it doesn't matter where you find that substance. It doesn't matter where you find that substance, whether it's in outer space or whether it's in deep within the dirt, the ground. If it is a substance like methane, it doesn't matter where I find it, it's going to be 1 carbon and 4 hydrogen. So again, the other one was mixtures. This is a diagram of a homogeneous mixture and a heterogeneous mixture. Again, the composition of a first of all, there's more than 1 substance. Now, a homogeneous mixture means just simply that it is uniform throughout the material. Now, it doesn't mean that it's at the that there's the exact same quantities of different substances or of the substances. It doesn't mean that there's exact quantities of the substance. Think about it. Tea. There's an opportunity to get unsweet tea and sweet tea. And there's, within the sweet tea realm, there's slightly sweet to really sweet. All of that is dependent upon how much sugar is in it. But it's still homogeneous because the composition is uniform throughout. Whereas a heterogeneous mixture is one where the composition is going to vary from location to location. This is just examples of homogeneous and heterogeneous. So let's look at some examples. Now, folks, you got to think about things. So, gold-plated jewelry. Is it an element, a compound, a homogeneous mixture, or a heterogeneous mixture? Gold-plated jewelry would be a heterogeneous mixture. Why? Exactly. If you have gold-plated jewelry, you can think it. I have gold-plated jewelry. If I were to break the jewelry open, I would probably see some sort of dark metal in the center and the gold plating on the outside. It is not uniform all the way through. What about platinum? Platinum is an element. It's found on the periodic table. It is element number 78 on the periodic table. How about carbon dioxide? It's a compound. At this point in time, I'm going to have to give you the formula. You're not expected to be able to come up with these formulas. Don't worry, that's coming. That's coming in chapter 4. Chapter 4 is going to be brutal. But as of right now, you will be given the formula if it's a compound. What about a bowl of cornflakes and milk? Is it an element, compound, homogeneous mixture, or heterogeneous mixture? It's heterogeneous because I can separate the cornflakes from the milk. They're not going to be uniform throughout. And what about tea? I've already mentioned tea multiple times. It's homogeneous. You will have, I think it's 5 of these on the test where you have to determine, is it an element, compound, homogeneous, or heterogeneous mixture? You don't have to memorize how to spell the words because it's multiple choice, but you will have some on the test. Questions about matter? Okay. Let's get into those atoms a lot more. We are going to spin. So the way this book is primarily arranged, we're going to spend 3 chapters just talking about the atoms of the element and getting to know the atoms of the element. Then we spend a few chapters getting to know compounds and how they're arranged and their formula and their name and so on and so forth. Then, starting around chapter 7, we actually start doing the transformations associated with these things, meaning chemical reactions. So again, we're going to start with these atoms of the elements. You should have watched the video. And you should have found out that there are 3 subatomic particles in every atom of an element. There is the proton, the neutron, and the electron. We will represent the proton when we're drawing or diagramming the atom of an element as a positive charge because it carries with it a +1 charge. We will diagram electrons as a negative charge because they carry with them a -1 charge. And in this particular case, the neutron is diagrammed as a circle with no charge. In these subatomic particles, you will notice that the protons and the neutrons are in the center of the atom of the element. That center of the atom of the element is referred to as a nucleus. The electrons are in the electron cloud surrounding the nucleus. Now, it's too hard to read, so I'll read it out. A proton. We will represent protons also with the letter P. Again, a proton carries a +1 charge. It is found in the nucleus of the atom of the element. A proton is responsible for the identity of the element. The number of protons in the nucleus determine the identity of the element. You change the number of protons in the nucleus, you're changing the identity of the element. And to be quite honest, there's not a way to change the number of protons in the nucleus without doing nuclear fission. Fusion. And only then are we, what we're doing is we're colliding to at a really high speed and velocity, and they wind up combining. But just in general life, you can't change an element's identity. But you can't change the number of protons. Now, if we were to talk about the mass of a proton in the terms of grams, we would be talking about 1.673 times 10 to the -27 grams, meaning that the mass of a proton is extremely small. Let's face it, I don't really want to work with 10⁻27 if I don't have to. So instead, we talk about a proton in terms of atomic mass units, and one proton has roughly an atomic mass unit of 1.00728, or in other words, 1. The neutron, we will represent with a lowercase n. It has no charge. It is also found in the nucleus of the atom of the element. The neutrons are responsible for a specific isotope of the element. That's their entire job, is they determine what isotope you have. Do you have regular hydrogen? Do you have what's called so hydrogen in water? If it's just regular water, it's regular hydrogen. Or is it heavy water? If it's heavy water, that means that we've used deuterium. Deuterium has a neutron in the nucleus of the atom. Okay, so I always tell my age with this one. How many people saw, I think it's Spider-Man 3 with Tobey Maguire. And his foe was Doc Ock. What they needed was tritium. Tritium is just another form of hydrogen, but it varies by the amount of neutrons in the nucleus. So it's an isotope of hydrogen. Okay, then we have the electron. The electron carries a -1 charge. Folks, the subatomic particle that we work with when we cause a reaction to occur, when we create compounds, when we create ions, the subatomic particle that is responsible for all of that is the electron. The electron is found in the electron cloud. Now, I forgot to mention the neutron in atomic mass units, 1.00866 AMUs, which is roughly 1. The electron is 0.0005 AMUs. You will notice that the majority of the mass of an atom of an element is due to the protons and the neutrons. The majority of the mass of an atom of an element is due to the protons and neutrons and not the electrons. Okay. Again, getting to know the periodic table. On the periodic table on the wall, it's in the top right-hand corner. On the periodic table that you're going to receive on the test, it's in the top left-hand corner. But that number, that whole number, is referred to as the atomic number. And the atomic number is equal to the number of protons. Again, it's the protons that determines the identity. So if I look up there and look at element 47, that element is Ag, which is silver. It always has 47 protons. Every single silver atom has 47 protons. Again, it's constant between atoms of the same element because it is responsible for the element's identity. Since we are talking about the symbol on the periodic table, just a few things about these symbols. Number one, again, the atomic number is in the top, it's usually at the top of the periodic of the square on the periodic table. That is the atomic number represented with a capital Z. It represents the number of protons. The next thing you're going to see is the atomic symbol. Every single element up here has its own unique symbol. If the symbol consists of only one type of, is only one letter, that letter will be capitalized. If the symbol consists of two letters, the first letter will be capitalized, the second letter will be lowercase. Notice that they are printed and not cursive. I don't do cursive when writing element symbol. Now, this number at the bottom is the average atomic mass. It is the average atomic mass. It is not the mass number. I want to reemphasize that because my daughter went to a school where they told her that number at the bottom of each square on the periodic table not only represented the average atomic mass, but it also represented the mass number. That is false. The mass number and the average atomic mass are two different things. The mass number, A, is equal to the number of protons plus the number of neutrons. Folks, the mass number is a whole number. You can't have a half of a proton. You can't have a half of a neutron. They are whole units, so it's a whole number. It varies between atoms of the same element because the number of neutrons vary. Questions so far? So far, I've introduced the subatomic particles of protons, neutrons, and electrons. And I've introduced the atomic number and the mass number. Again, isotopes result from the atoms of the same element having different numbers of neutrons. Okay, so how do we know how many neutrons it has? If the number of neutrons in an atom of an element can vary, how do we know how many neutrons it has? Well, the answer is through the isotope symbol. One variation of the isotope symbol takes the atomic symbol of the element and as a superscript to the left of the atomic symbol, they list the mass number. And then as a subscript to the left of the atomic symbol, they list the atomic number. So this is one variation. So for example, carbon, the most abundant element of or the most abundant isotope of carbon is carbon 12. What this symbol is telling me is that I am working with carbon, element number 6 on the periodic table. That's its atomic symbol. I know the mass number. The mass number is 12. That's the number of protons plus the number of neutrons. And I know the atomic number. The atomic number is 6. That's the number of protons. So carbon 12 has 6 protons and 6 neutrons. Now, in a neutral atom of an element, neutral means that the charges balance each other out. If protons are positive and electrons are negative, that means you have to have the same number of protons as you do electrons, and therefore it's 6 electrons in a neutral atom of an element. Now, I will admit, this variation of the isotope symbol has 2 things that are repetitive. I don't need both the atomic symbol and the atomic number. Because if I have the atomic symbol, I can look at the periodic table and see the atomic number. So the atomic number and the atomic symbol are actually repetitive. You don't need both pieces of information. You need just the one, which is the atomic symbol. So another isotope of carbon is carbon 14. I could write carbon 14 in this variation, yes, but again, the atomic symbol and the atomic number, that's very repetitive because I can simply look at the periodic table and get the atomic number. So the other way we can write it is just the element symbol with the mass number. You will always have to include the mass number on an isotope symbol because the number of neutrons vary. So we know that carbon 12 and carbon 14 are isotopes because they are both carbon, but their mass number varies, meaning the number of neutrons varies. Whereas this had 6 protons, 6 neutrons, and 6 electrons. This one has 6 protons, 8 neutrons, and 6 electrons. There is one more way, and this one is written a lot of times in textbooks because it's easier. And that is to include the atomic symbol -12 instead of trying to make superscripts. This means the same thing as that previous slide. It's just another way of writing it. So how will you see this on a test? You will be given a a table that you have to complete. That table will ask for the element symbol. It will ask for the isotope symbol, and you can choose any of the 3 isotope symbols that you want to choose. It will ask for the number of protons, the number of electrons, the number of neutrons. It will ask for the mass number, A, and it will ask for the atomic number, Z, and then it will ask for the average atomic mass. So, this first one, difficult to read. I gave you the symbol sulfur 3416. That's all I gave you. What's the element symbol? It's simply S. How many protons does it have? 16. I know that from 2 different things. Number 1, in this particular case, I gave you the atomic number. But I also could have looked over at the periodic table and gone, okay, S is 16, so it's 16. In a neutral atom, how many electrons will it have? 16, because they have to be equivalent. How many neutrons does it have? Remember that the mass number, A, equals number of protons plus number of neutrons. So if you have 34 as the mass number, that's equal to 16 plus the number of neutrons. So how many neutrons does it have? 18. Yes. Yes. The difference is I'm at this point, I'm calling it a neutral atom of sulfur, whereas what you are describing is an ion of sulfur. So that's why they're different, is because of whether it's neutral or whether it's an ion. The mass number. Again, I have to give that to you, or I have to give you the information you need to get it. So what is the mass number? 34. What is the atomic number? 16, because it's equal to the number of protons. And what is its average atomic mass? 32.06. That came from the periodic table. I go ahead and make you do that column because I want you to realize that the mass number and the average atomic mass are different. Okay, the next one. I gave you A, this is A, by the way, and this is Z. I gave you A of 37 and Z of 17. What piece of information do I want to start my process with? The 37 or the 17? 17. So what does 17 mean? It's the atomic number, which means it's chlorine. What else does it mean? It means there's 17 protons. What else does it mean? 17 electrons. How does the 37, what do I need to do with the 37? I will take that 37 and minus 17, and that will give me my number of protons. Excuse me, my number of neutrons. So there are 20 neutrons. But what else does that tell me? My isotope symbol, which is going to be chlorine 37. And then where do I go to get my average atomic mass? Periodic table, which tells me it's 35.45. The next one, I gave you the number of protons and the number of neutrons. What does the protons tell me? The atomic number? What else does it tell me? Number of electrons? What else does it tell me? The symbol, which is magnesium. The 14, what am I going to do with it? I'm going to add the protons and the neutrons to get 26. What is that 26? That tells me my isotope symbol. And then magnesium is 24.31. Yeah. Do the last two. Okay, on the next to last one, you should have found out that it was ruthenium 99. Ruthenium is element 44. So therefore, its atomic number and its number of protons is 44. I gave you the mass number, and from that mass number, we were able to take that 99, subtract out 44, and you got 55. And it's 101.07 according to the periodic table for the average atomic mass. The last one I gave you silver 109. That's telling you everything you need to know. First of all, Ag. Ag is element 47 on the periodic table, so that's 47 protons, 47 electrons, and 47 is its atomic number. The 109 tells me specifically the mass number. So I took that 109, subtracted out 47, and got 62. And then it had a mass of 107 an average atomic mass of 107.87. Two things. Number one, you will notice that in every example, I either gave you the isotope symbol, the mass number, or the number of neutrons. I have to give you one of those pieces of information because you are not expected to know what isotope it is without that information. Second thing is, while it may not be in this exact order, because I can't remember what order I put it in, yes, you're going to see a table just like this on the test with, I believe it is 5 different problems. Normally, each square runs a half a point to a point, so you can see how understanding this is going to add up on your test. Questions? I don't have time to start the average atomic mass, plus I believe this is where I said I was going to stop for the day. So that is the good news. Hopefully you've got everything you need. I expect of the stuff I go over on Tuesday, if you want to get a jump start on studying for your test. I know I have a big mouth, but I'd really would rather not talk over a bunch of packing up. Number one, I expect to go ahead and have you calculate the average atomic mass on the test. So that's something I'm going over Tuesday that I expect will be on the exam. The other thing I expect will be on the exam that I'm going to go over on Tuesday is how to determine the number of protons and electrons in an ion, which we will be using that other periodic table I gave you. I'm not going to put the stoichiometry on the test, so I will check, meaning I'm not going to have Avogadro's number on this test. So I won't go, I'll still plan to go over it Tuesday, but that little bit will be on the following. So that if you do decide to do a jump start, you can study those 2 extra things from the videos. And then we'll go over it in class on Tuesday and hopefully solidify it for the test. I will see you on Tuesday. This video will get posted sometime this weekend, but I'm headed to a conference. Literally, I'm walking out the door after I finish class. So it will be good question. Yes. Send me an email with the exact number, and I'll actually go and look at your specific homework. If it is correct, then I'll do some, I'll report the problem, and I'll also do your effect. Okay, thank you.
It's way right.
Yeah, you can use any of the three. I just cheat and make it as fast as possible.
For the like bolded elements that we have to memorize in the charges, do we need to be able to list them, like say like, okay, like lithium, helium, et cetera, have a charge of one, or can we just like be able to find them on the table and know?
You can't, so on the table, one of the things I'll go over is this is +1, that's +2,
Yeah.
that's +1, 2, 3.
Yeah, and that, like, I
And
can
then-
memorize all those shapes and everything, but do I need to be able to like list off each of
No.
these? Okay,
Cause you're gonna get this periodic table on the.
okay, yeah. I
So
can kinda
you
like-
just have to know where it falls
Okay.
on the periodic
Got
table.
it. That makes it a little easier.
That was just me trying to give you a picture of the ones
Yeah.
I wanted you to know.
I was gonna ask you, I accidentally like messed up. I figured out what I did, but instead of doing, I think it was 45,
44?
yeah, 44, I ended up down here at 99 because I went off of
You went off of the mass
Yeah.
number and put the mass number as.
and when I was down here, I saw this. Is that the absolute value? Like,
Okay,
how
so
does that work?
we cannot. We are unable to capture
Some of those,
for any length of time,
yeah,
the different, to know if it has different isotopes.
my
But for the most part, these being all man-made, starting. So the ones that have a single value, those again come from the fact that they were man-made.
and they only exist for like a few seconds under extreme circumstances.
Right.
Yeah, my chemistry teacher taught me that, and I wasn't sure if that's what that was.
That's why they only have a single number.
Because it didn't make much sense that there would be an absolute value of them.
Well, and again, it's because we can't capture it long enough to actually determine if it has isotopes, and only if it has isotopes. Only if it has isotopes, is it gonna have something other than a whole number.
Okay. Thank you.
Mm-hmm.
How you doing?
I'm good, how are you?
Good. What's your name?
Faith Yarberry,
I'm Braxton. Nice to meet you.
nice to meet you. I will get out of y'all's hair.
You should say we have a quiz today.
We do have a quiz. I walked in. Ooh,